Welcome to The Explainer. Today, we are tearing into Chapter 3 of Heinz Aerosol Technology to really master uniform particle motion. If you're getting ready for a PhD defense, consider this your boot camp. We're going to build an expert-level understanding of this stuff so you're ready for any question they throw at you.
Okay, so here's our game plan. We're going to start with the two fundamental forces that are always battling for control over a particle. Then we'll build up the perfect, ideal model for how particles move, and then, like good scientists, we're going to pick it apart and correct it for the messy real world. After that, we'll get into the universal metric that lets us compare apples to oranges, and finally, we'll see how it all plays out in actual real-world systems.
So, first things first. To get a handle on how any particle moves through a gas, you've got to understand this fundamental conflict. It's a constant tug of war between two forces, inertia and viscosity. One of them is always in charge. And this slide lays out the two big players perfectly. On one side, you've got Newton's law. This is for the big, fast stuff, like cannonballs. Here, inertia is king. The main source of drag is just the sheer effort of shoving air molecules out of the way. But on the other side, in the world of tiny, slow-moving aerosols, it's a whole different ballgame. Here, Stokes's law reigns, and it's all about viscosity, the sticky friction of the air itself. So the obvious question is, how do you know which law to use? Well, that's what the Reynolds number is for. It's basically a scorecard that tells us which force is winning the battle. And for us, in the world of aerosol science, this is the kicker. The Reynolds number is almost always less than 1. That means we are firmly, and I mean firmly, in Stokes's territory. Okay, so we know we're living in the world of Stokes' law. Let's dive in and really master the foundational equation that runs the show here. And here it is. It looks so simple, right? But don't let that fool you. This little equation is a powerhouse. It's actually derived from the super complex Navier-Stokes equations, but it boils down to this. The drag force is just a product of the fluid's viscosity, the particle's speed, and its diameter. This is the starting point for pretty much everything. Okay, now if you're prepping for a defense, lean in because this slide is gold. These 5 assumptions are the bedrock of Stokes' law. You need to know them inside and out. Why? Because they define the perfect ideal world where the law works flawlessly. And more importantly, they are the exact weak spots where reality kicks in and we need to make corrections. Trust me, you will get asked about these limitations. Right, because let's be honest, the real world is messy. Particles are not perfect little spheres floating around in an infinite empty space. So we need some tools in our toolbox to adjust Stokes's law to match what's actually happening out there. So here's problem number 1 with our ideal model. What happens when particles get really small? I mean, so small, they're about the same size as the average distance between air molecules? Well, that no-slip assumption we just talked about, the one that says air sticks to the particle's surface, it completely falls apart. So what's the fix? It's something called the slip correction factor, and it's pretty much what it sounds like. A tiny particle can literally slip between the gas molecules, kind of like a motorcycle weaving through stopped traffic. It feels less resistance, less drag. This means it actually settles faster than Stokes' law would predict on its own. The slip correction factor, CC, is just the number we use to account for that extra slip. All right, on to challenge number 2, shape. You know, a perfect sphere is a nice idea in a textbook, but it's not reality. In the real world, we're dealing with jagged pieces of dust, long chain-like fibers, clumpy messes, you name it. And to handle that, we use the dynamic shape factor, symbolized by the Greek letter chi. Think of it as a kind of aerodynamic handicap. It's just a simple ratio that tells us how much more drag our weirdly shaped particle has compared to a perfect sphere that has the exact same volume. Now, here's the thing you have to burn into your memory. This factor is pretty much always greater than 1. What does that actually mean? It means your irregular, real-world particle is going to feel more drag. It's going to settle more slowly than a nice, smooth sphere of the same volume would. This is a super important point for any aerosol researcher. So let's just stop and think about this for a second. We have particles of all different sizes, different densities, and all these funky, irregular shapes. It's a total mess. How on earth are we supposed to compare them fairly? We need some kind of universal yardstick. And that yardstick, the thing that brings order to all this chaos, is the aerodynamic diameter. And I'm not exaggerating when I say this is probably the single most practical, most important concept in the entire field. So here's the genius of it. The aerodynamic diameter lets us completely stop worrying about what a particle is actually made of or what its real shape is. Instead, we just ask one simple question. If this particle were a perfect little sphere of water, what diameter would it need to be to settle at the exact same speed? That's it. It gives us one single number to describe its behavior, no matter how physically complex it is.
Let's just walk through it real quick. You start with your complicated, irregular particle, right? Like a piece of quartz dust. We don't care about its real shape or density for a second. We just see that it settles at a certain speed. Then, we find its aerodynamic twin, a perfect sphere with the density of water that settles at the exact same speed. The diameter of that simple sphere, that is the aerodynamic diameter of our complicated piece of dust.
All right, so now we have this amazing universal metric. Let's put it to work. Let's see how all this theory actually applies to real systems and the instruments we use every day to study them. One of the first and most fundamental things we can do with all this is calculate a particle's terminal settling velocity. This is just the constant speed a particle reaches when the drag force pushing up on it perfectly balances the force of gravity pulling it down. And for aerosols, you have to remember they reach this equilibrium speed almost instantly. Now, how a whole cloud of these particles behaves depends entirely on whether the air is moving or not. In perfectly still or tranquil air, they all settle down together, kind of like a falling blanket of gust. But in a stirred room, which, let's be real, is most situations, the concentration is uniform and just slowly and exponentially decreases everywhere at once, never quite hitting zero. And look, this isn't just theory for a textbook. These very principles, settling velocity, aerodynamic diameter, they're the engine behind a whole bunch of real instruments that scientists use to measure, sort, and classify aerosols all the time. And this quote from Hines really nails why this all matters. The concepts we've just covered, especially aerodynamic diameter, aren't just for exams. They are absolutely fundamental to almost every practical application you can think of, from designing better air filters to figuring out how pollution gets into our lungs. So, as we wrap this up, and as you get ready for that defense, I want to leave you with a question to chew on. Now that you know how to take the ideal model and correct it for the messy reality of slip and shape, what real-world aerosol system are you now equipped to analyze with confidence? Because being able to bridge that gap from the perfect textbook case to the complex real world, well, that's what makes you an expert.